Hi, everybody. So rather than giving you a longer, more complex example of how to integrate a, a specific PDF function that's in multiple parts into a CDF, I thought it might be helpful for some of you just to point out a general pattern that you'll find whenever you're integrating a PDF with multiple parts into a CDF with multiple parts. As I've tried to point out in class and hopefully convinced you of an examples, you have to be very careful in these cases to getting your limits of integration right. And so, but if you sort of remember a simple rule, then you'll always be able to get your limits of integration right, and you won't be able to go through a lot of extra steps. So generically, I've said that if you have some PDF that is of the form f of x is equal to a bunch of pieces. So I'm just going to make this generic. So imagine that f of x has a piece up here that I'm going to call f1 of x that is defined from some lower bound, I'll call L1 of its interval, all the way up through the lower bound of the next interval. And then it might have an f of 2 of x might be on the next interval, which will be from L of 2 all the way up to L of 3, and then maybe there's a third interval, and that'll be from the lower bound of that interval all the way up to, we'll just call the lower bound of the fourth interval, even though there's not a fourth interval here. So it might be that this guy is minus infinity, and it might be that this one is infinity. So this is a very generic definition of the way in which a PDF might be cut up into pieces. Now, I've already told you that that what you end up doing is something along the lines of saying, well, my f of x is minus infinity to x of f of u du. So I am just going to have to cut that up into going from L1, which could be minus infinity in this case, all the way up to L2 of f1 u du plus L2 to L3 of f2 u du plus L3 to L4 of f3 u du, where I guess this last one I'll actually make equal to x, assuming that, for the case where x is between L3 and L4. And then if you did all that, you could do this part separately from this part, separately from this part. Now, what I'm hoping you'll see by now is that this part right here, well, here I'll do, is that this small part here is actually just big F of L2. And this slightly bigger part right here is actually big F of L3. And so the tip that I have for you, the very general tip that you can take from that, is that when you're building your f of x function, your big f of x, in these pieces, then the ranges will always be the same. So this will be from L1 to L2. This will be from L2 to L3, and this one will be from L3 to L4. That in each one of these cases, it's just going to be big F of L1 plus the integral from L1 to x of little f u du. So down here, it's the same pattern. Big F, but now we use L2 And now we take the integral from L2 to x, f of u du. And then down here, we do f of L3 plus the integral from L3 to x, f of u du. And that's the basic pattern. Most students usually do something that they usually get most of this column right on their own, although the limits of integration they often forget. And then the next thing they forget is to include these contributions that come from the previous pieces. But if you just remember this basic formula for all of the pieces, this formula right here, then you don't have to go through a lot of extra effort. Just for every piece, remember that you just take the big F of the lower bound, which you would have already derived, and then you integrate from that lower bound to x of whatever little piece you're looking into. And what I mean by you'll already know this piece here is that we already know ahead of time, because it's a CDF, that f of negative infinity is equal to 0. And so this f of negative infinity that's equal to 0 is basically the first one of these that's implicitly in the first row of every CDF. So every CDF is effectively going from minus infinity to x of the PDF in that early region, where this early region goes from negative infinity up to whatever the breakpoint is for the next region. So there is implicitly this f of negative infinity that is hanging out in front of there. And we say, by convention and by definition, that a CDF has to be equal to 0. Its limit has to be equal to 0 as you go all the way out to negative infinity. So that should mean that if you start with the first piece of a PDF here, then you should be able to generate its CDF with this formula just by plugging in a 0 when you do big F of the lower bound, where the lower bound is going to be minus infinity, and then you'll integrate this from the lower bound up to x, and then when you go to the second piece, then the big F for the second piece will end up being effectively the integral of all of the first piece. And so that's a simple formula that can hopefully get you through that. Okay, I hope that makes sense.